Welcome to this coding walkthrough. Today, we'll be tackling LeetCode problem number 2030, smallest k-length subsequence with occurrences of a letter. This problem challenges us to craft the lexicographically smallest subsequence of a given length while meeting specific constraints. We'll explore the problem step by step, break down the approach, and analyze the solution. Let's get started. The problem asks us to find the lexicographically smallest subsequence of a given string S, with a fixed length k. This subsequence must include a specified character, letter, at least repetition times. A subsequence is formed by removing some or no characters from a string while preserving the order of the remaining characters. For example, from the string ABC, AC is a valid subsequence. To solve this, our output must satisfy all the given constraints. The subsequence has to be exactly k characters long, include the letter at least the specified number of times, and be lexicographically smallest, meaning it must be the smallest in dictionary order compared to all other valid subsequences. The problem ensures that the input is well defined, so we won't encounter cases where the conditions are impossible to satisfy. Let's explore an example to understand the problem better. Given the string S is leet, k is 3, letter is E, and repetition is 1, we need to find the smallest subsequence of length 3 that includes E at least once. The possible subsequences of length 3 are le, let, and et. Among these, only EET is lexicographically smallest while fulfilling the condition of including the letter E at least once. Therefore, the output for this example is EET. Now, consider another example with S as LeetCode, k is 4, letter is E, and repetition is 2. Here, the subsequence must be of length 4 and include the letter E at least twice. Valid subsequences that meet this requirement include ect, ed, and others. Among these, the one that is lexicographically smallest is ect, so the output is ect. Another example to consider is when S is cac, k is 3, letter is B, and repetition is 2. In this case, the subsequence must have a length of 3 and include B at least twice. Among the valid options, the lexicographically smallest subsequence is bab. In terms of constraints, the length of the string S can go up to 10,000, so we need an efficient approach. The subsequence length k must be between 1 and the length of S, and the number of times the letter must appear, represented by repetition, must be at least 1 and at most k. Additionally, we must account for edge cases. For instance, if k is equal to the length of S, the result will simply be the string S itself since no characters can be deleted. If repetition equals k, the subsequence will consist only of the letter repeated k times. These constraints and edge cases help define the bounds of the problem. Another important edge case occurs when the string S does not have enough occurrences of the letter to satisfy the repetition constraint. In this scenario, the problem guarantees that the input will always be valid, so we don't need to handle such cases in our solution. By keeping these constraints and edge cases in mind, we can now focus on developing an efficient algorithm to solve the problem. The key is to maintain the lexicographical order while ensuring the subsequence length is exactly k and the required occurrences of letter are included. To solve problem number 2030, the goal is to find the lexicographically smallest subsequence of length k that includes the specified character letter at least repetition times. This requires balancing three key constraints: maintaining lexicographical order, ensuring the subsequence has exactly k elements, and guaranteeing that letter appears enough times. One approach we could consider is the brute force method. The intuition here is straightforward: generate all possible subsequences of length k from the string, filter those that meet the condition of having at least repetition occurrences of letter, and then pick the smallest one based on lexicographical order. However, this approach is computationally impractical. With a time complexity of O2 to the power of n, for generating all subsequences, the exponential growth quickly makes this method infeasible for even moderately large strings. While conceptually simple, the trade-offs in performance make it unsuitable for this problem. A more efficient option is the greedy approach using a monotonic stack. The idea here is to traverse the string while maintaining a stack that builds the smallest possible subsequence of length k. The stack ensures lexicographical order by allowing us to remove elements if the current character is smaller and if removing those elements doesn't violate the constraints of subsequence length or the required occurrences of letter. To make informed decisions, we also track the remaining occurrences of letter in the string. This helps determine whether it's safe to skip or remove certain characters. The time complexity of this approach is O(n), as each character is pushed and popped from the stack at most once, making it highly efficient. While this method is optimal in terms of time, it does require precise handling to ensure the constraints are met. Overall, it strikes a great balance between efficiency and correctness, making it a very promising approach. The chosen strategy for this problem is the greedy approach using a monotonic stack. This method stands out because the stack naturally maintains lexicographical order, and the greedy strategy ensures we process each character only once, resulting in excellent time efficiency. By keeping track of the remaining occurrences of letter, we can make deliberate choices about when to skip or remove characters, ensuring all constraints are met. This approach also handles edge cases well, such as when letter is sparse or overly frequent in the string. Compared to brute force, which is computationally too expensive, and dynamic programming, which has higher complexity and implementation overhead, the greedy stack approach is both elegant and optimal. It provides the best balance of simplicity, efficiency, and correctness for this problem. In this problem, we're tasked with finding the lexicographically smallest subsequence of length k from a given string s, while ensuring that it contains the character letter at least repetition times. This means we have to simultaneously satisfy three constraints. The subsequence must be exactly k characters long, it must include at least repetition occurrences of letter, and it must be the smallest possible sequence alphabetically. To approach this, we leverage a few key insights. First, maintaining lexicographical order can be achieved using a monotonic stack, which allows us to build the subsequence in increasing order as we process the string. Second, because we need at least repetition copies of letter, we must keep track of how many occurrences are still available in the remaining portion of the string. This tracking will help us decide whether to keep or discard the letter as we go. Lastly, the length constraint is enforced by ensuring the stack never exceeds k elements, and we rely on a greedy algorithm to make the best choice at each step based on future constraints and the current state of our stack. To implement this solution, we rely on two key data structures, a stack and a counter. The stack is used to build the subsequence, ensuring that each character added adheres to the constraints while maintaining lexicographical order. We also use a variable to track the remaining occurrences of letter in the string, which helps us decide whether to keep or discard characters as we iterate. The algorithm begins with some initialization. We start with an empty stack, and we calculate the total occurrences of letter in the string, storing this in remaining _letter_ count. We also initialize a variable letter_in_ stack to 0, which tracks how many letter characters are currently in the stack. As we iterate through the string, we process each character one by one. For every character C, if it matches letter, we decrement remaining _letter_ count because there's now one less occurrence of letter left to process in the string. To maintain lexicographical order, whenever the top element of the stack is greater than the current character, we check if removing the top element would still allow us to construct a valid subsequence. Specifically, when considering removing the top element of the stack, we check two conditions. First, we ensure that removing it won't prevent us from building a subsequence of length k, which means the stack size plus the remaining characters in the string must still be at least k. Second, we ensure that removing the element doesn't break the repetition constraint. For example, if the top element is letter, we need to confirm that there are still enough letter characters remaining in the string to meet the requirement. If both conditions are satisfied, we remove the top element from the stack. Additionally, if the removed element is letter, we decrement letter_in_ stack accordingly. Next, we consider whether to push the current character onto the stack. If the stack size is less than k, we add the character. If the character is letter, we also increment letter_in_ stack. At every step, we carefully evaluate edge cases, such as ensuring the stack doesn't exceed the required number of letter characters or verifying that the remaining portion of the string can still meet the repetition constraint. Finally, once we've processed all characters, we return the first k characters of the stack as the result. To analyze the algorithm's efficiency, we start with its time complexity. Each character in the string is pushed onto the stack at most once and popped at most once, giving us a time complexity of O(n), where n is the length of the string. The space complexity is O(k), as the stack holds at most k elements, which represent the subsequence. Let's walk through an example to clarify how the algorithm works. Suppose the input string is s equals a back, with k equals 3, letter equals a, and repetition equals 2. We initialize our variables as follows: an empty stack, remaining underscore letter underscore count equals 2 because there are 2 occurrences of a and s, and letter underscore in underscore stack equals 0 since the stack is initially empty. As we process the string, these values will be updated based on the algorithm's rules. We start processing each character in the string. The first character is a, so we push it onto the stack, update the stack to a, increment letter underscore in underscore stack to 1, and decrement remaining underscore letter underscore count to 1. The next character is b, which is pushed onto the stack, resulting in a, b. The third character is another a. Since the stack size is still less than k, we push it onto the stack, update the stack to a, b, a, increment letter underscore in underscore stack to 2, and decrement remaining underscore letter underscore count to 0. Now, the stack is full, so we skip the next 2 characters, c and b, as adding them would exceed the required length. At the end, we return the first k characters of the stack, which is ABA. This example demonstrates how the algorithm balances constraints while maintaining lexicographical order. Edge cases include scenarios where k equals the length of s, making the solution simply s, or cases where repetition exceeds k, which makes it impossible to form a valid result. These edge cases must be handled appropriately to ensure correctness. Here, we define the function smallest subsequence within the solution class. It takes 4 parameters: the string s, the desired subsequence length k, the target letter, and the repetition count that specifies how many times the target letter must appear in the result. We start by initializing an empty stack to build our subsequence and calculate letter underscore count, which holds the total occurrences of the target letter in the string. The variable n stores the length of the string for future reference. Next, we loop through each character in the string, tracking both the character and its index. Inside the loop, we use a while condition to check if the current character is lexicographically smaller than the top of the stack, if removing the top character still allows us to form a valid subsequence of length k, and if the stack is not empty. If the top character of the stack is the target letter, we also ensure that enough instances of the letter remain to meet the required repetition. If these conditions are met, we remove the top character from the stack, incrementing the repetition count if the removed character is the target letter. This ensures we maintain the correct number of the target letter in our result. Now, we check whether the current character can be added to the stack. If the stack's length is less than k, we proceed. If the character is the target letter, we append it to the stack and decrement the repetition count, since we're fulfilling one of the required occurrences. Otherwise, if the remaining space in the stack is greater than the remaining repetition, we add the character to the stack as well. After this, if the current character is the target letter, we decrement letter underscore count to track how many instances of the letter are left in the remaining part of the string. Finally, after completing the loop, we return the stack as a string by joining its elements. This ensures we get the smallest subsequence of length k that includes the required occurrences of the target letter. We start by importing the necessary classes and defining our solution class. The method smallest subsequence takes 4 parameters: the input string s, the desired subsequence length k, the target letter, and the required number of occurrences of that letter, repetition. Inside the method, we use a stack to build our subsequence. Additionally, we initialize a variable letter count to track the total number of occurrences of the target letter in the input string. To calculate this, we iterate through each character in the string and increment letter count whenever the current character matches the target letter. Next, we prepare for the main iteration over the string, where we'll construct the subsequence. The variable n holds the length of the input string, which will help us manage indices efficiently. The for loop begins by iterating over each character in the string. For each character, we check conditions to decide whether it should be added to or removed from the stack. One important condition is ensuring lexicographical order. If the current character is smaller than the top character of the stack, we consider removing the top character, provided that doing so does not prevent us from forming a valid subsequence of length k. We also ensure that removing a character doesn't reduce the count of the target letter below the required repetitions. If the character being removed is the target letter, we need to check whether there are still enough occurrences of it remaining in the string to satisfy the repetition condition. If not, we break out of the loop and stop removing characters from the stack. Otherwise, we increment the repetition variable because we're allowing room for one less target letter in the subsequence, and then we remove the top character from the stack. After handling removals, we evaluate whether the current character can be added to the stack. We ensure that the stack size does not exceed k, as the subsequence must be exactly of length k. If the current character is the target letter, we push it onto the stack and decrement the repetition variable, reflecting that we've added one occurrence of the target letter. If the current character is not the target letter, we still allow it to be added, but only if there is enough room in the stack to satisfy the remaining required occurrences of the target letter. After processing the current character, we decrement letter count if it matches the target letter, as we've accounted for this character during the iteration. Finally, we construct the result string by iterating through the characters in the stack. Using a string builder, we append each character in the stack to form the final subsequence. Once the string is fully built, we return it as the result. This ensures that the output is the smallest possible subsequence of length k that contains the required number of occurrences of the target letter. With this implementation, we maintain an efficient and structured approach to solving the problem, leveraging the stack to manage lexicographical order and the constraints around the target letter. Starting with example 1, we are given the input string a target subsequence length of 3, the letter a as our priority, and a requirement that a appears at least 2 times. Initially, our stack is empty, and we know the string contains 2 occurrences of a out of its total length of 5. Now, we begin processing each character in the string. At index 0, the character is a. Since the stack is empty, we append it to it and decrement the repetition count to 1 because we've added one of the required a's. At index 1, the character is b. Here, we add b to the stack because the stack length is still less than 3, and we ensure there's enough space left in the stack to meet the repetition requirement. At index 2, the character is it again. Since a is our target letter, we prioritize it and append it to the stack. This fulfills our repetition requirement for a, so the repetition count becomes 0. At indices 3 and 4, the characters are c and b, but we skip both because the stack is already full with 3 elements, which matches the required length. This completes the processing for this example. The final output for example 1 is the subsequence ABA, which is the smallest lexicographical sequence of length 3 that includes at least 2 occurrences of the letter a. Moving on to example 2, we have the input string abcap, a target subsequence length of 4, the letter C is our priority, and a requirement that C appears at least once. Initially, the stack is empty, and the string contains 2 occurrences of C across its total length of 6. At index 0, the character is a, and since the stack is empty, we append a. At index 1, the character is b. We append b as well because there's still space in the stack and no immediate need to prioritize C. At index 2, the character is c. Being the target letter, we append it to the stack and decrement the repetition count to 0, as we've now met the requirement of 1c. At index 3, the character is a. We skip this character because adding it would leave insufficient space to meet the required length of 4. At index 4, the character is c again. However, since the repetition requirement for c has already been fulfilled, we skip this character. Finally, at index 5, the character is b. We append b to the stack to complete the subsequence of length 4. The stack now contains a b, c, and b, which satisfies all the problem constraints. The final output for this example is ab. Now, in example 3, we consider a case where all characters in the input string are the target letter. The input string is AAAAA, and we need a subsequence of length 3 that includes the letter a at least 3 times. Initially, the stack is empty, and the string contains 5 occurrences of it in total. The length of the string is also 5. Let's begin processing this example. At index 0, the character is a. Since the stack is empty, we append it to it and decrease the repetition count to 2. At index 1, the character is it again, so we append it to the stack and decrease the repetition count to 1. At index 2, the character is it again, and we append it to the stack, reducing the repetition count to 0. Now the stack is full with 3 elements, which matches the required length. For the remaining indices, 3 and 4, the characters are both a, but we skip them since the stack is already full. The final output for this example is AAA, which is the smallest lexicographical subsequence of length 3 containing exactly 3 occurrences of the letter A. To analyze the time complexity of the solution, let's break it down step by step. First, the operation s.count letter scans through the entire string to count the occurrences of a specific letter. Since this involves visiting each character in the string once, it takes n time, where n is the length of the string. Next, we have the main iteration, which involves a for loop that processes each character in the string exactly once. This loop also contains a while loop responsible for adjusting the stack. Importantly, each character can be pushed to or popped from the stack only once during the entire process. Therefore, the total stack operations, including all pushes and pops, are bounded by n. Additionally, the conditional checks performed within the while loop or if statements involve constant time operations, O1. These checks do not affect the overall complexity since they are insignificant compared to the n operations. Together, these components form the foundation of the algorithm's efficiency analysis. Now, let's discuss the final step, which involves constructing the result. Here, the stack is converted into the final string using the join operation. This step takes time proportional to the size of the stack, which is at most k, the length of the required subsequence. Thus, this step adds an k component to the time complexity. When we combine all the steps, the dominant terms are the counting operation and the single traversal of the string, both of which are n. Therefore, the overall time complexity of the solution is n. Shifting focus to space complexity, the stack is the main contributor. Its size is limited to k, meaning it uses k space. Other variables such as letter underscore count, repetition, and n occupy constant space, which is 1. Additionally, the input string s and the parameters k, letter, and repetition do not contribute to extra space usage as they are inputs rather than created data structures. This gives us an overall space complexity determined by the stack, which is k. To summarize the space usage, the stack is the dominating factor, leading to a total space complexity of k. Now, let's examine the algorithm under different scenarios. In the best case, the while loop executes rarely, such as when all characters are in lexicographical order or the stack never exceeds the constraints. Here, the overall time complexity remains n, because the dominant cost is iterating through the string. In the average case, the while loop executes a moderate number of times, but since each character is still pushed and popped from the stack at most once, the complexity does not change and remains n. Even in the worst case, where the while loop executes for every character, such as with a reverse lexicographical order requiring frequent popping, the time complexity is still n, because every character can only be processed once in the stack. So, regardless of the case, the time complexity remains linear, n. Finally, let's compare this approach to a brute force solution. A brute force method would involve generating all possible subsequences of length k and filtering those with the required number of occurrences of the target letter. Afterward, the smallest lexicographical subsequence would be selected. This process involves generating n choose k subsequences, which is exponential and computationally infeasible for large inputs. In contrast, the given algorithm solves the problem optimally in n time and k space, making it significantly more efficient. To mathematically verify the big O analysis, note that every operation within the loop is bounded. Each character in the string is processed exactly once, and the while loop pops each character at most once, meaning the total stack operations are n. The s.count letter operation is also a linear scan, contributing n. Finally, the result construction step is k, which is negligible compared to n for large inputs. Consequently, the overall time complexity of the algorithm is n, and the space complexity is k, confirming its efficiency. When solving this problem, there are some common mistakes to watch out for. For instance, one frequent error is ignoring the requirement that the letter must appear at least a specified number of times in the subsequence. Simply returning any subsequence of length k will fail if it doesn't meet this condition. This requirement is a core part of the problem, so skipping it leads to invalid solutions. Another issue is neglecting the lexicographical order. It's not enough to just satisfy the constraints, the subsequence must also be the smallest in lexicographical order. This means you need to carefully compare characters as you process the string. Finally, overlooking edge cases can lead to incorrect results. For example, consider when k is the same as the string's length, or when the repetition value is 0. These scenarios often behave differently, so you need to handle them explicitly to avoid runtime errors or inaccurate outputs. Another common pitfall is using inefficient data structures or approaches. For example, repeatedly iterating through the string to check constraints can lead to a time complexity of n squared, which is impractical for larger inputs and may cause the solution to time out. Instead, you should strive for an optimized approach. Additionally, maintaining the correct stack state is critical. One mistake here is failing to remove elements from the stack when a smaller character is encountered, which can prevent the subsequence from being the lexicographically smallest. Similarly, mishandling the count of the required letter can result in subsequences that don't satisfy the problem's constraints. Getting these details right ensures both correctness and efficiency in your solution. To approach this problem effectively in an interview setting, there are a few key insights to keep in mind. First, this problem is a variation of the monotonic stack pattern, which is widely used for selecting subsequences while maintaining constraints. Recognizing this pattern can help you structure your solution more effectively. It's also important to be prepared to discuss edge cases, such as when the repetition value exceeds the total occurrences of the letter in the string, or when the string contains only one unique character. Interviewers often test your ability to handle these scenarios. Time complexity analysis is another critical aspect. Your solution should ideally run in O(n), as string manipulation problems often require efficiency. Lastly, be ready to explain the trade-offs of your approach. For example, you might be asked why a greedy method using a stack is preferable to alternatives like brute force or dynamic programming. There are several related problems on LeetCode that share similarities with this one, making them great practice opportunities. For example, in LeetCode 3.16, Remove Duplicate Letters, you use a similar monotonic stack approach to find the smallest lexicographical subsequence. Another example is LeetCode 10.81, Smallest Subsequence of Distinct Characters, which also focuses on maintaining the smallest lexicographical order. LeetCode 4.02, Remove K-Digits, applies similar logic for forming the smallest number by maintaining a stack. Finally, LeetCode 3.21, Create Maximum Number, represents a more complex variation where you need to merge subsequences optimally. Exploring these problems can deepen your understanding of the patterns and techniques used in this type of challenge. In addition to the monotonic stack approach, there are other methods to solve this problem, although they come with trade-offs. For instance, a brute force approach involves generating all subsequences of length k, filtering those that meet the repetition requirement, and then sorting them lexicographically. While this guarantees correctness, it is extremely inefficient due to its exponential time complexity, making it unsuitable for large inputs. Another option is dynamic programming, where you use a DP table to track subsequences of length k while maintaining constraints. This method can be effective but often involves higher space complexity compared to the monotonic stack approach. Finally, a greedy approach with sorting involves sorting the characters lexicographically and attempting to build the subsequence from there. However, this method doesn't guarantee optimality when constraints like repetition must also be satisfied. These alternatives highlight why the monotonic stack is often the best balance between efficiency and simplicity for this problem. Great job! We've covered the key steps to solving this problem, including the greedy approach and stack usage for optimization. Remember, mastering these techniques is crucial for solving similar challenges. Thanks for watching, and stay tuned for more coding insights. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!